Hi, my name is Surya and I do PhD at NTNU. Today I'm going to talk about recursive training based physics inspired neural network for electric water heater modeling. And this is how I'm going to present. Start with the introduction, then motivation, then briefly about PINN and single zone model, and finally training procedure, and then results, finally conclusions and future works. It is very well known that the renewable energy share in the grid is rapidly increasing. However, the intermittent and distributed nature of the renewable energy is pose some threat to the grid stability. So, are traditional approaches alone enough to solve these challenges? Absolutely not. We need combination of different solutions to achieve 100% renewable share in the grid, among which demand-side flexibility has lot of potential and also cheaper if tapped efficiently. Demand-side flexibility is a concept in which uh, end-user appliances are controlled to solve the grid problems. Among different appliances, electric water heater has gained a lot of attention, mainly because it is power intensive and has thermal storage capability. Different studies has shown the potential of electric water heaters for demand side flexibility. So how does it work? End user usually provides access to the appliance in exchange for financial or other incentives. So great, right? Problem solved. Everyone is happy, right? Not really. There are really some there are really some challenges in implementing it. First, cost-effective automation. It is very expensive to install sensor in each water heater to control it. So why do we need sensor? To ensure user comfort and to avoid bacteria growth. So I think it is really important to acknowledge this importance of end user satisfaction for demand side flexibility success, because otherwise if it is not ensured, then end user might not be interested in giving access to the appliance. So devising control strategy to ensure user comfort triggers estimating future water temperature. So in essence, we need thermodynamics model. There are different modeling techniques available, but each modeling techniques has some drawbacks. For example, white box modeling requires complete information, and gray box modeling are computationally intensive, and black box model requires huge amount of data to train. So the research question we are trying to solve is, how can we develop a computationally efficient high accuracy model without temperature sensor? So neural network models requires huge data to develop a model, but it is computationally cheap. Differential equation model requires less data, but it is computationally expensive. What if we can combine this both to get a model that requires less data and also computationally efficient? Physics inspired neural network allows us to do that. When you combine the neural networks and the physics, you get physics inspired neural network. This work aims to provide a proof of concept of such approaches for electric water heater thermal model. So before going into PIN training, the physics used in this work is presented here. We used a single zone model to develop the PIN. Single zone model assumes uniform water temperature inside the tank. And it is based on energy flow analysis. The ordinary differential equation representing single zone model is here. So how can we integrate this domain knowledge into neural network? The physics can be integrated either through loss functions or through architecture. In this work, we used both techniques to integrate the domain knowledge. First, loss function. So this is the physics-based loss function in which then during training, the neural network will try to reduce the difference between the gradient estimated using differential equation and the gradient estimated using neural network, so that neural network can learn the physics behind the single zone model, physics behind the single zone model. And this is the proposed architecture for electric water heater. This is similar to normal neural networks. However, the initial layers are structured in such a way that it mimics the differential equation. As you can see, there is subtraction between atmospheric temperature and the previous temperature and multiplied with the system parameter. And this is similar to here, like G into temperature minus T ambient. So this is the training procedure to obtain the final model. I would like to remind here that our goal is to develop a model without temperature sensor. We assume that we have access to the power consumption data. So we start with the power consumption data, we estimate the parameters, and we estimate the average hot water demand. And this is estimated using the technique proposed in the reference file, average water demand. Once you estimate the average water demand, you separate the on and off events. Um, in this work, we used two models, one for on dynamics and one for off dynamics, mainly for convenience. So we separate the on events and off events, and we train the on dynamics model and the off dynamics model separately. Once the models are trained, you combine them and you simulate the electric water heater using the trained models for, for future events. After simulation, you can obtain the temperature and power data. So we evaluated our approach using real-world data set, power consumption data for an electric water heater from Pecan Street data port is selected to evaluate the approach. 50 random once the parameters were estimated and the water demands were estimated. After that, 50 random events for on dynamics and off dynamics models. 50 random events were used for training the on dynamics and off dynamics model each. So this is the result. After training, we evaluated the performance of the PINN. As you can see from the table, the mean absolute error for on dynamics model is only 0.25 degrees Celsius. And from the graph, you can see it is similar to differential equation model. For off dynamics model also, the case is similar. Mean absolute error is 0.15 degrees Celsius, and the graph shows PINN has comparable performance. So these are the tests within a thermostat control region. However, during flexibility activation, the temperature goes beyond thermostat control region. So we evaluated the model performance beyond thermostat control region. As you can see, PINN and PINN has similar performance to differential equation model, both for on dynamics and off dynamics outside the control region as well, outside the control region as well. So finally, we combined both on dynamics and off dynamics model and simulated the model for for two different scenarios with the different water demands. So these are the results. As you can see, PINN closely follows the differential equation model, and the inferred power consumption for the power scenario also has the same case. So this is the results for the second scenario. As you can see, there is little bit lag in PINN prediction. This is mainly due to the prediction propagating error due to recursive prediction. However, this is the general well-known issue in recursive predictions, and there are some methods to rectify it as well. So we calculated the performance metrics as well. As you can see, PINN has really close performance. PINN has similar performance to differential equation model and has high accuracy. So the results indicates that it is possible to replace the differential equation model, which is computationally expensive, with physics-inspired neural network model, which is computationally cheaper and has the same performance. So that is the goal, to get a model which is computationally efficient and also accurate. In this case, for this work, we used only single zone model, which is not really that accurate, but as a starting point, we used it as a starting point. But one can use the similar approach to develop the high accuracy model. So conclusion, the framework for developing PINN-based electric water heater simulation model with only historical power consumption data is presented. The proposed approach has comparable performance to traditional single zone differential equation model. The employability for flexibility modeling is also demonstrated. So our future work will focus on incorporating stratification effects into PINN, improving loss function and the PINN architecture, and methods to reduce propagation error. The main takeaway from this work is that it is possible to develop a model without temperature sensor, and it can be computationally cheaper. And yes, that's the main takeaway. You can combine the neural networks and the differential equation model to develop a computationally efficient, high accuracy model that can ensure end user comfort. Thank you. So these are the references, my bio and contact. That's it. Thank you very much.